Hi everyone, welcome to this channel, Best Science Brain YouTube channel. Today we are taking a look at a topic in physicochemistry, chemical kinetics. And the aspect of chemical kinetics we're going to look at is rate of reaction. This particular topic is meant for students in high institution, in tertiary institutions, those in their first year and those in their second year of high institution. We've been doing this topic. If you are not subscribed to the channel, kindly move off to the channel's name as the video is playing now. Look up or move off to the channel's name, Best Science Brain. Under the channel's name, you're going to see a subscription icon. Tap on the subscription icon only once as the video is playing and get subscribed to the channel for more video notifications. Also, to understand the concept of this tutorial, the best thing to do is to download the video and take your time to study with us as we teach on this tutorial. Turn your notification button on if you are subscribed, so that you'll be seeing or getting notifications for subsequent videos. Share our videos to students in tertiary institutions that require this topic. So we're now going to rate of chemical reaction. In chemistry, reactions occur at different rates. The word rate here can be interpreted as speed or velocity. Some reactions take few seconds to be accomplished. Some reactions take few minutes to be accomplished. Some reactions take many minutes, while some reactions take hours, days, or even years to be accomplished. For instance, if I set a piece of wood shavings on fire, it may take few minutes to be accomplished. If I pour powdered limestone or grinded limestone into an acid, it may take just few minutes or space of seconds to be accomplished. If I expose hydrogen peroxide to sunlight, it may take some minutes to be accomplished. So some reactions occur very fast, while some reactions occur very slow. So when we talk about the different speed at which reactions take place, we are referring to rate of reactions. So let's go to what we have. It says chemical reactions occur at different speeds or rates. Wood shavings burn faster when set ablaze compared to an equal mass of a log of wood. So when wood is in powder form, as I said, it burns faster compared to log of wood. 2.0 grams of powder limestone is observed to react faster with 2 molar HCl acid compared to 2.0 gram of marble chips, meaning limestone lumps, in 2 molar HCl acid. A piece of sodium dropped inside cold water reacts almost explosively compared to a piece of calcium dropped into cold water. These differences in the rates or speeds of chemical reaction led to the concept of chemical kinetics. So we are giving examples of different reactions or similar reactions that occur at different speed, like wood shavings burn faster than also wood that is in lump. Powder limestone react faster than marble chip. Marble chip means limestone in lumps or larger size. Sodium, which is a metal, react faster in cold water compared to calcium, which is also another metal, drop inside cold water. So what are the reasons for these differences among similar substances? That is what is meant by a rate of reaction, which we're going to explain in a few minutes. Now, factors affect the rate of reaction. So what factors affect the rate of chemical reaction? We have 1, temperature. Temperature affect of reaction system. When a reaction system is heated, the reactant molecules will gain higher kinetic energy or higher velocity. As a result, they will start moving faster. And this movement or higher velocity will lead to higher rate of collision or higher frequency in the rate of collision. The molecules will collide more frequently among themselves and with the walls of the container. This collision leads to breakage of bond in the reactants and formation of bond in the product. Therefore, if you increase temperature, the rate of reaction will increase. Number 2 factor is concentration of reactants. The term concentration here means quantity of reactants. So how do we increase concentration of reactants? By adding more reactants into the reaction system, increasing the amount of reactants in the reaction system. It's more like you're adding, you have 2 cubes of this illustration is more like you have 2 cubes of sugar in a cup of tea. You now go and add extra 4 cubes of sugar, making it 6 cubes in the same cup of tea. The net effect is that the particles of sugar will be more plenty compared to how they were initially. And then that will result to overcrowding. The reactant molecules will be overcrowded in the same space, and that will lead to more collisions. And collisions, being effective, will lead to greater rate of reaction. Then pressure of gaseous reactant. Pressure affects only gases. Only gases. Pressure has no effect on solids or liquids. So, how do we increase the pressure of gases? From Boyle's law, pressure is inversely proportional to volume. That means to increase pressure, I have to decrease the volume of the container. How do I decrease the volume of the volume of the gaseous system? Sorry, not container. How do I decrease the volume of the gaseous system? Is by compressing the gas or the gaseous volume. Compressing the gaseous volume. Since gases have large intermolecular space in between them, so when you compress the gaseous system, the molecules will get close to each other and they will collide more frequently, leading to higher rate of reaction. Going to surface area of reacting particles, we explained initially some reactions that occur faster than others. Example, wood shavings, which we used before. As an example, when set ablaze, burns faster than a log of wood. Why? Because the wood shaving, the particles are smaller in size, and the particles will be exposed to the surface of reaction more than the log of wood that will take time for fire to consume it. So the wood shaving is said to have a larger surface area. Powder limestone. Powder limestone reacts faster than marble chip or limestone that is in lump, because in powder form, the particles are exposed to the reaction site. All the particles will be exposed to the reaction site. That means powder limestone have larger surface area than limestone in lump. So surface area I talk about putting particles in small sizes or in grinded form or in powder form for them to react faster. So nature of reactants. As we also use an example, when I use sodium, I say sodium reacts faster in cold water compared to calcium. The two are metals. So why would sodium react faster? Because sodium possesses higher energy or is more electropositive, is more reactive than calcium. That is why sodium reacts faster than calcium when both of them are treated by equal amount of the same hydrochloric acid. And the example is iron can displace hydrogen from dilute HCl. When you drop iron inside HCl, iron can displace hydrogen from the acid, but copper cannot displace hydrogen from dilute acid because iron is more electropositive than hydrogen and can push hydrogen away from acid, but copper is less electropositive than hydrogen and cannot push hydrogen away from acid. So if you visit the electrochemical series, you see, or what called activity series, you see that iron is placed higher than hydrogen and is more reactive than hydrogen. So you can push hydrogen away from dilute acid, but copper cannot. Then presence of catalyst. A catalyst is a substance which alters or which changes the rate of chemical reaction but remains unchanged at the end of the reaction. So a catalyst can either speed up or can retard or slow down the rate of chemical reaction. We have positive catalysts which speed up reactions. We have negative catalysts which retard reactions. A positive catalyst speeds up reaction by decreasing what we call the activation energy. The activation energy is nothing but the minimum amount of energy required by reactants to form products. So it will decrease this energy and make the reaction to occur faster. While a negative catalyst will increase the activation energy and slow down the rate of reaction. They will have light, presence of light. Some chemical reactions occur only in the presence of sunlight, or sunlight makes them feasible. So such reactions are said to be photochemical or photolytic reactions. Example is the splitting of water during photosynthesis. So the light phase of it, in which light is required to split a water molecule, which is called photolysis of water. And the example is also hydrogen peroxide decomposes in the presence of sunlight into water and oxygen. And the example is silver nitrate decomposes into silver, oxygen, and nitrogen 4 oxide in the presence of sunlight. So these reactions are facilitated by sunlight. The next is orientation of reactants. So the orientation of reactant refers to the way reactants are positioned before collision. So orientation matters. If the reactant molecules have correct orientation, collision will become effective. But if they have a wrong orientation, collision will become ineffective. So effective collision only leads to reaction, while ineffective collision does not lead to chemical reaction. Derivation of rate equations from the stoichiometry of a chemical reaction. We call it the theoretical rate law or equation. So the theoretical rate law or rate equation is a rate equation derived from a balanced chemical equation. It's not derived from experiment. So this is the theoretical rate equation. So we're going to look at how we can derive the rate equation from a balanced equation, or when we're given a balanced equation. So we'll go on. Here we define the rate of reaction. The rate of a chemical reaction is defined as the change in the concentration of substances. The substances could be reactants or products per unit time. So this is the accurate way of defining rate of reaction. The rate of reaction is defined as the change in the concentrations of substances, and the substances could be reactants or products per unit time. So that is how to define rate of reaction. We now say, let us consider the hypothetical chemical reaction given below. So let that example done, A plus B giving us C plus D represent a chemical equation, where capital A and capital B are the reactants and capital C and D are the products. So you can see where capital A and B are reactants and C and D are products. So should this be a balanced equation, how then do we write rate equations for this equation? So let us go on. The rate, that is R, of a reaction is directly proportional to the concentration of the substances. So the rate of reaction is proportional to the concentration of the reactants and that of the products. So say hence we can write the rate equation of each substance as follows. So the first equation says R means rate, is equal to negative D, that D is called delta or change. Then square bracket opens, inside it capital A. So that square bracket in chemistry where A is placed is called concentration. That bracket means concentration. It's a symbolic way of representing concentration in chemistry. So when you have bracket A is pronounced concentration of A all over dt, meaning change in time. So equal to K, then square bracket A there. So let's go back to that. That R means rate. And from definition of rate, we say that rate is the change in concentration per unit time. That is, dA means change in concentration of A, all over dt meaning change in time. And we know that rate is proportional to concentration. So it's equal to, we have a concentration of A on the other side. And then K is the rate constant. Then that is for reactant A. For reactant B, similarly, we have equation 2, R equal to negative D, meaning change, square bracket B, meaning concentration of B, change in concentration of B all over dt, that is change in time, equal to the rate constant K multiplied by the concentration of B in bracket, because rate is proportional to concentration. Now, if you look at equation 1 and 2, both are written for the reactants A and B, and they bear negative sign. So you can look at the reactants once again, A and B. So the equation 1 and 2 are equations, rate equations for respect to the reactants A and B. Now, why are the equations bearing negative sign in front of the change sign, D sign? You have minus minus for these two equations written for reactant A and reactant B is because the reactants are being depleted as the reaction progresses. So as the reaction continues, the reactants start vanishing, they're being used up. So that minus sign shows that the reactants are being used up as the reaction progresses. So we have the negative signs on equation 1 and 2 show that the concentration of reactants decrease with time as the reaction proceeds. Okay, let us now write the same rate equation for the products. Writing the rate equation with respect to the products, we have R equal to plus delta, that is change D, concentration of C all over dt equal to Kc. So this is for the product C. And then for product D, R equal to plus change, that is small d, concentration of D in bracket, that is square bracket, then D inside it, all over dt equal to K, then multiplied by concentration of D. So as we have said before, the letter small d means change. The square bracket with the substance inside it means concentration of that substance in it. Then dt means change in time. So rate is proportional to concentration. We now have concentration on the other side with the rate constant multiplying it. Then if you look at the product, equation 3 and 4 for the product, they are carrying positive sign in front of the change symbol. So why is this positive? But the reactants were negative. The products are assumed to be positive because as the reaction progresses, more products are being produced. So the amount of products continue to increase while the reactants continue to decrease. So because the products are increasing as the reaction progresses, we now have a plus sign written on that in front of that change symbol, that is D symbol. So as observed above, there is no negative sign on the rate equation because the concentration of products increase with time. So that one will have a positive sign for the products. Now let's continue. If the chemical reaction involves stoichiometric coefficients, then each concentration term in the rate equation will be divided by its stoichiometric coefficient. Let us consider the hypothetical example given below. So let's look at this reaction. In this reaction, we'll have some numbers in front of the reactant, 3 and 4, and some numbers in front of the products, 5 and 2. These numbers are which normally called number of moles. We can still call them stoichiometric coefficients. Unlike the former example I used, where you have A, B, C, and D. The former example I used, they only have one mole in front of the substances. You can see that. That's the former example. But this present example will have a different stoichiometric coefficient in front of the substances. How then do we write the rate equation for each of the substances? We still follow the same process we observed before to write rate equation by dividing the change in concentration of each substance by the change in time. Then the next we'll do is to divide the change in concentration by each of the coefficients as we have in the balance equation. For example, the rate equation for these substances are connected as follows. So for the first one, we'll write negative because the reactant, D meaning change, then square bracket A, that is change in concentration of A, all over change in time, that is dt, then divided by, we multiply the change in time by 3. So we have 3 under. So why the 3, or how come the 3? The 3 is the 3 moles of A, 3 in front of A. Going to B, we write negative change in concentration of B, all over change in time, that is dt, then divided by 4. Since we have 4 moles of B, 4 in front of B, equal to 4C, change in concentration of C, that is dC, all over dt, divided by 5 moles of C. But remember that C, the sign in front of the D is positive because C is a product. Then for D, similarly, we have positive because being a product plus change, that is small d meaning change, concentration of D, that is D in bracket, all over dt, divided by 2, that is 2 moles in front of D. So when you have different stoichiometric coefficients in front of the substances, you have to divide the change in concentration of each of the terms by the number of moles or the stoichiometric coefficient present or as given in the balance equation. We'll now go to a live example. Say the catalytic oxidation of ammonia is given by the equation shown below. Write the rate equation that connects all the substances in the equation. We have 4 molecules of ammonia plus 5 molecules of oxygen, giving us 4 molecules of nitrogen 2 oxide or nitrogen monoxide plus 6 molecules of steam. So how do we connect all this? Based on what you have learned so far, solution rate equal to D, that is change, bracket opens, ammonia, bracket closes, change in concentration of ammonia all over, change in time divided by 4. Because of 4 molecules of ammonia there, divide the concentration, the numerator by 4. Then go to oxygen, negative because the reactant as well. Change in concentration of oxygen, that is D, oxygen in bracket, then all over dt divided by 5 because of 5 moles of oxygen in the balance equation, equal to going to the product plus, because it's a product we're trying to express, D, that change concentration of NO in bracket NO, bracket closes, all over dt divided by 4. I have 4 moles of NO there. Then equal to D, that is change in concentration of steam, that's H2O in bracket, all over dt, that change in time, divided by 6, since there are 6 moles in the balance equation. So you see, that confirms the examples or the illustration we're given before now. So having done that, we are all these equations written in this one from the balance equation, we call them the rate equation, theoretical rate equations, because they are obtained from balance equation. We now go to experimental rate equation or rate law. Rate equation derived from experiment or from experiment is different from the one derived from chemical equation. So rate equation derived from chemical equation, which is now called theoretical rate equation, which we studied above, sometimes are not always correct in chemistry, but the rate equation derived from experiment are taken as being correct because they are derived as a result of series of experiments and reaction mechanisms that have been studied. So experimental rate equation is somehow different from theoretical rate equation. And now we want to look at experimental rate equation, how to write it or how to derive it. So we say this is an expression which connects the rate of reaction R to the constant of the reactants. Okay. The experimental rate law or equation differs from the theoretical rate law or equation discussed above due to the effect of certain factors on the rate of reaction. And these factors include temperature, effect of catalyst, the reaction mechanism. Nevertheless, the experimental rate law gives a more precise and accurate measurement of rate of reaction than the theoretical rate law derived from the reaction stoichiometry. So the rate law derived from experiment is more accurate than the one derived from balance equation. So let's continue. The rate R is directly proportional to the concentration of the reactants, as we have said before. Now let us consider the hypothetical example given below. So look at that reaction that involves that small letter A and B. Small letters A and B represent the stoichiometric number of moles or coefficients. Capital A and capital B are the reactants, while C that is above the R represent the catalyst, and they have the products formed on the right hand side. So we have it reads where capital A and B are reactants and C is the catalyst. The rate of reaction R is directly proportional to the concentrations of A, B, that is the reactants, and that of the catalyst C. So rate of reaction is proportional to the concentration of A, B, and C. We can put the thing mathematically, all this the relationship mathematically as shown below, where R represents rate. They have the proportionality sign, proportional to concentration of A, then concentration of B, and then concentration of C, as you have there. So we now introduce the rate constant to be able to remove the proportionality sign, bring in a constant. So we'll say introduce the rate constant K and some special exponents Q, R, and T. We have the rate equation or the experimental rate equation. So you introduce K, we now have R, remove the proportionality sign. We now bring in K, and then we have to introduce some special exponents or powers. We raise A to the power Q, we raise B to the power R, we raise C to the power T. So those exponents Q, R, and T are called order of reaction. So we write the special exponents Q, R, and T on the constitution terms in the rate equation represent the order of reaction with respect to each substance. So Q is the order of reaction with respect to reactant A, R is the order of reaction with respect to reactant B, and T is the order of reaction with respect to the catalyst. So this is the general form of rate equation for an experimental rate law. So this is experimental rate law or experimental rate equation, the way it looks like. It brings in the order of reaction. The theoretical rate law, with studied above, does not bring in the order of reaction. So I have no provision for the order of reaction in its expression. We'll now move over to order of reaction. Order of reaction, this is defined as the exponent or power to which the concentration terms are raised in a given rate law or equation. So let us consider the rate law given below. So the order of reaction is the exponent or power to which the concentration terms are raised in a given rate law. So let's look at this example. R equal to K, then A raised power Q, B raised power R, and C raised power T. So this is a rate equation or experimental rate equation. So What do the terms, those powers Q, R, and T stand for? They are the order of reaction. Q is the order of reaction with respect to reactant A. R is the order of reaction with respect to reactant B. And T is the order of reaction with respect to reactant C. So you can see that. What do you mean by order? Now, the overall order of reaction is the sum of the respective order of reactions. So we want to know the overall order of reaction. We'll add the exponents. We'll add Q, R, and T. That give us the overall reaction order. Now we'll now go to types of reaction order. So we say depending on the sum of the exponents on the concentration term in a given rate law, we have the following types of reaction order. We have zero order reaction or zero order kinetics, first order reaction, second order reaction, third order reaction, fractional order reactions, and higher order reactions. So these are the different types of reaction order we have in chemistry. Let's start with zero order reactions or kinetics. So this is the chemical reaction in which the exponent on the concentration term in a given rate law or rate equation is 0. That means when the concentration term is raised to power 0, we have zero order reaction. Hence, the rate of reaction of a zero order reaction is equal to the rate constant. So in a zero order reaction, rate of reaction and the rate constant are equal. And the rate of reaction does not depend on the concentrations or concentration of the reactants. So let us consider the hypothetical unimolecular reaction given below. So look at that reaction that involves only one reactant particle, one reactant, that is 1 mole of A. Any reaction that involves only 1 mole of the reactant is called a unimolecular reaction. So let's say A gives rise to product. And let's say the rate law for that reaction given by R equal to K multiplied by A constant of A, that is A inside square bracket. If the constant of A is raised to power 0, that means this reaction is called zero order reaction. So the concentration term, which is A, used in the rate equation, is raised to power 0. We can now say that this reaction is zero order reaction. And in mathematics, any value raised to power 0 is 1. So A raised to power 0 is equal to 1. They will now have R is equal to K because A will now vanish, being 1. That means in zero order reaction, the rate of reaction R and the rate constant K are equal. The two are equal. That means the rate of reaction does not depend on concentration in zero order reaction. So we'll now move on. A plot of rates of reaction against concentrations obtained from a zero order reaction will give the graph below. So if you plot the rate of reaction against concentration for a zero order reaction, as you can see on that fig, you have this kind of graph. Why is the graph moving horizontally? It's because the rate does not depend on concentration. So whatever the concentration is, the rate remains the same value. So this is the plot of zero order reaction. So having done that, we'll now move to first order reaction or first order kinetics. In a first order reaction, the exponent or the power on the concentration term in the given rate law or rate equation will be equal to 1. That means the concentration of the substance that appears in the rate law will be raised to power 1. So the rate of reaction R therefore is directly proportional to the concentration of the reactant. So considering the unimolecular reaction given below, so let's look at this. A going to product where A is the reactant. If the rate law or the experimental rate law given as R equal to K multiplied by constant of A. Look at that expression, R equal to K times constant of A, that's A inside square bracket. The power to which A is raised, we are seeing nothing there. What it means that A is raised to power 1. The power is 1. That means for this expression, we have a first order reaction because the concentration of the substance is raised to power 1. Remember in the former example we used, A was raised to power 0. That was called zero order reaction. So the power to which the substance is raised to determines the order. If raised power 0, it is 0 order. Raised power 1, first order. Raised power 2, second order. So you can see that. So a graph of the rate of reaction against concentration A for a first order reaction gives the shape below, while the gradient or the slope of the graph is the rate constant K. So if you plot the rate of reaction against concentration for a first order reaction, we have a straight line linear graph of this nature, because the rate depends on concentration. So as the concentration of A increases, the rate also increases. The slope of the graph, which the change on the vertical axis, change on R axis over change in concentration axis, will give us the rate constant for that reaction. Okay, so we now move to second order kinetics or second order reaction. In a second order reaction, the exponent on the concentration term in a given rate law or equation is 2, or the sum of exponents on the concentration terms in the given rate law or equation is equal to 2. So let's explain what is meant by a sum of exponents. So let us consider the unimolecular reaction depicted below. So let's look at the same unimolecular reaction we'll be using as example. This time around, rate is equal to K multiplied by the constant of A. The power to which A is raised to is 2. So that is why it's called a second order reaction. So that is it. So we now say if the reaction is bimolecular, that means if the reaction involves two reacting particles. Remember that if a reaction involves only one reacting particle or one mole of reacting particle, we say it's unimolecular. But if it involves two moles or if it involves two reactants, we now say that it is bimolecular reaction. So we say if the reaction is bimolecular reaction, then the concentration terms of each reactants A and B must be raised power 1 as shown below. So let's explain this. So this is an example of bimolecular reaction because it involves two reacting particles A and B, one mole of A and one mole of B, that is giving you 2. That is why it's called bimolecular reaction. So for this reaction, for it to be second order, the expression goes thus: R equal to bringing the two reactants, concentration of A and then concentration of B. Each of them raised power 1. So first order for A and first order also for B, because each of the reactant concentrations raised power 1. So if you add the powers of the power of A, the exponent of A to the exponent of B, 1 is 1 plus 1 give you 2. That to make it second order also. But if the reaction is unimolecular, that involves only one reactant, then the power on that reactant must be 2, as we have in the previous example. But if it involves two reactants that are indeed bimolecular, then the two reactants will appear and each of them will have the power 1, 1. They add the 1, 1, you have 2. You see the same second order reaction. So the reaction is first order with respect to A and first order with respect to B. So reaction order becomes first order, that is 1 plus 1. First order for each of them giving us second order for a bimolecular reaction. Okay? Then going over to third order kinetics. In third order reactions, the exponents on the concentration term in the given rate law or equation is 3 for unimolecular reaction, or the sum of the exponents on the concentration terms is 3 for a bimolecular or a thermolecular reaction. We introduce another kind of reaction called thermolecular reaction. Thermolecular reaction is a reaction that involves 3 reacting particles. Okay, let's continue. So let's look at this one. Is the unimolecular reaction A giving us product involving one reactant. So it's going to be third order when R is equal to K, then concentration of A raised power 3. That is third order. Then next example, A plus B giving us product being a bimolecular reaction. The bimolecular, the rate will now be equal to K constant of A raised power 2. So for bimolecular reaction, A plus B giving us product. So this is bimolecular because two reactant particles are involved. 1 mole of A and 1 mole of B, giving us 2 moles. Now for this to be third order reaction, we look at the equation 1, R equal to K, constant of A raised power 2, and constant of B raised power 1. That means in this first expression, the overall order is 2 on A plus 1 on B, giving us 3. That is third order. And the rate of reaction is, for A is second order and for B is first order. If you want to find the overall order, you add the two powers, 2 plus 1, giving us 3. Or it can be written as R equal to constant of A raised power 1 and then constant of B raised power 2. That means first order respect to A and second order respect to B. So that will still give you 1 plus 2, giving us 3. So when you have a bimolecular reaction, for it to be third order, either of the particles will be raised to power 2, while the other one will be raised to power 1. So we say in equation 1, the order of reaction is second order with respect to A, as you can see, and first order with respect to B, as you have there. Why in the reverse is the case in equation 2? In equation 2, the order is 1 respect to A and 2 respect to B. In both cases, the overall order of reaction for each equation is 2 plus 1 or 1 plus 2. That gives you 3. Third order reaction. Then we now have this reaction A plus B plus C product. This reaction involves 1 mole of A, 1 mole of B, and 1 mole of C, giving you 3 moles in all. So reactions are called thermolecular, not tri, thermolecular reactions. So the rate equation goes thus: if it's going to be third order, K, A raised to power 1, B raised to power 1, and C raised to power 1. So the rate equation, this rate equation. So look at this exercise that says the chemical reaction below had the given rate equation R equal to K multiplied by the constant of S raised to power 1 multiplied by the constant of Y raised to power 2. And the reaction is given to you as S plus Y equal to product. That means that reaction is a bimolecular reaction. What that is bimolecular, it involves 1 particle of A and 1 particle of Y, giving you 2 bimolecular. So the rate equation given to you as R equal to Ks, then Y to the power 2. We ask, what is the order of reaction with respect to each reactant in the given rate law? Then II, what the overall order of reaction? So go to the solution. We now write the rate equation once again down there. R equal to K multiplied by S to the power 1 and then multiply the constant of Y raised to power 2. So we want to find out the order of reaction with respect to each of the reactants. So the constant of S, denoted as square bracket opens S, then square bracket closes, is raised to the power 1, as you can see there. While the constant of Y, denoted as square bracket opens Y, square bracket closes, raised to power 2. And the reaction is first order with respect to S and second order with respect to Y. So the answer for S, the order is 1 because S raised to power 1. And for Y, the order of reaction to respect to Y is 2 because Y raised to power 2. So number 2 says we have to find the overall order of the reaction. We get the overall order of reaction, we'll add the exponents, the power of S and the power of Y. So we have 1 plus 2, that gives us 3. So the overall order is third order reaction. 1 plus 2 giving us 3, that is third order reaction. Go to the next exercise that says, consider the hypothetical reaction given below. That's the unimolecular reaction A, giving us product. And we are told if the rate equation given us change in constant of A, that is the A, over change in time, the time, equal to K. So this is the rate equation for the above reaction there. We ask what is the order of reaction. So we'll now go to the solution and see what it says. Solution. So we'll have this dA over dt equal to k. So this is the rate equation. So we have, it reads that both expression is the rate equation in our problem. But recall that the rate of reaction, that is R, is the rate of change in concentration of substances per unit time. It then follows from the above equation that R is equal to change in dA over change in dt. So the expression dA over dt is something as the rate of reaction. So we can present or replace dA over dt by R. So that means going to this reaction or this expression, dA over dt can be replaced with R, because that dA over dt is the change in concentration per unit time, which is the rate of reaction. So hence we can write R equal to K, that replacing dA over dt by R, that means R becomes equal to K. Now, seeing the rate of reaction is equal to the rate constant, so you see that in this expression, like the last expression, R is equal to K, the rate is equal to the rate constant, and that makes it zero order reaction or zero order kinetics. Because in the zero order reaction, the rate of reaction and the rate constant are equal, and the rate does not depend on any concentration. Look at the right hand side of the equation. After close to K, there's no other value given to you. So R and K are equal, making it a zero order reaction. Now going to order versus molecularity of reaction. Are they the same thing? No. The order of a chemical reaction has been treated above and defined as the exponent or the sum of the exponents of the constant terms in a given rate equation. Thus, we have zero order, first order, second order, and third order fractional and high order reactions or kinetics. So the order of a chemical reaction is not determined from the stoichiometry of a balanced equation. This means that the order of a chemical reaction does not correspond to the number of reactant molecules unless by coincidence. The order of chemical reaction is determined by experiment or experimentally. So what am I saying here? What I'm saying is that the order of reaction has no business with chemical reactions or chemical equations. Has no business with the number of moles that appear in the chemical equations. It is different from the stoichiometric coefficient. It is being determined by experiment. So order of reaction is a value obtained by experiment from the reaction mechanism and other factors. So it's not determined by using the reaction stoichiometry. So that is order of reaction. So let's just take a view from what we have done before to show that order of reaction and the stoichiometric number of moles are not the same. So let's look at the example we are taking before that involve A and B reacting. Where capital A and B, they are the reactants, and C is the catalyst. Then the small letter A and small letter B are the stoichiometric number of moles or the coefficients, number of moles of reactants in the balanced equation. Now let's look at the experimental rate law written down there as R equal to A raised to power Q, B raised to power R, and C raised to power T, because the rate of reaction depends on the concentration of the reactants A and B, and of course of the catalyst C. So you see that A raised to power Q, B raised to power R, and C raised to power T. If you go to the balance equation, the letters Q, R, and T didn't appear in the balance equation. And then if you look at the number of moles, small letter A and small letter B did not appear on the experimental rate equation. So Q, R, and T are called order of reaction. So you see that the order of reaction has no business with the stoichiometric coefficient. They are different from the two. So order of reaction does not appear in the stoichiometric doesn't appear in the chemical equation. It is different from the number of moles on the balance equation. So small letter A and B are the coefficients or number of moles, and they don't appear, or they did not appear on the rate equation. What you have, the power raised, or which A, B, C are raised to, are order of reaction, different from the stoichiometric coefficients. So order of reaction is a different thing obtained by experiment. So we don't use stoichiometric coefficients in determining the actual experimental rate equation. No, it's not used unless you are talking about theoretical rate equation. So we're now going over to what is meant by reaction molecularity. So we say, on the other hand, the molecularity of a reaction is defined as the number of atoms or molecules of all the species participating in the reaction in the reaction as given by the stoichiometric equation. So molecularity of reaction is obtained from the balanced chemical reaction. So it's not obtained experimentally. So see the differences. So we have the three different types of reaction molecularity. We have unimolecular reaction, a reaction that involves one molecule or one atom of the reactant. Bimolecular reaction, a reaction that involves two molecules or two atoms of the reacting particle. Thermomolecular reaction, a reaction that involves three molecules or atoms of the reactant. Hence, unlike order of reaction, molecularity of reaction is determined from the reaction equation or from the reaction stoichiometry. So let's look at this, what is meant by unimolecular. Look at that first reaction. We have only one particle of S or one mole of S giving us product. We call it, because of one mole of S involved, we call it unimolecular reaction. Let's call an example, S plus Y giving us product. We have one mole of S and one mole of Y, or one particle of S and one particle of Y, giving us two particles or two moles. We call that a bimolecular reaction. In the third example, we have two particles of S or two moles of S giving us product is also bimolecular. Bimolecular reaction that involves similar substance. Then we have thermomolecular reaction, two moles of S, that is 2S plus one mole of Y, or two particles of S and one particle of Y. 2 plus 1 gives you 3. Thermomolecular reaction. Then the last example there, we have 3S. That means 3 particles of S involving similar substances. 3S or 3 moles of S giving us product, also a thermomolecular reaction. We now say, to further distinguish molecularity and reaction order, let us consider the hydrolysis of sucrose, whose equation is given below. So we have sucrose hydrolyzed in water in the presence of acid. So we have the equation sucrose plus water giving us glucose and fructose. So when fructose is broken down by hydrolysis, we get the components of sucrose, which is glucose and fructose. So you look at the reaction, we have one molecule of sucrose and one molecule of water, and that made the reaction bimolecular reaction. So we say the above reaction is bimolecular reaction because two molecules of reactants are involved. Bracket opens, one molecule of sucrose and one molecule of water. However, the above reaction is not second order reaction. So you don't expect that because two molecules are involved or two moles are involved, one of sucrose, one of water, that the reaction is second order. No. Order is not obtained from reaction stoichiometry. We can get molecularity by looking at the number of reacting particles or the total number of reacting particles. However, the above reaction is not second order. It has been shown experimentally that the hydrolysis of sucrose shown above is a first order reaction, and the rate of reaction depends only on the concentration of sucrose. So this experimental rate equation for that reaction are equal to K multiplied by the concentration of sucrose C12H22O11 raised to power 1. So you see that in this reaction, the rate of reaction does not depend on the concentration of water, but only depends on the concentration of sucrose raised to power 1. So that reaction is first order. But in terms of molecularity, it is bimolecular. But in terms of reaction order, it is first order. So the order is determined by experiment and not by looking at the chemical equation. We have an exercise that says the decomposition of ethanol is given by the equation C3CHO, that is ethanol, decomposing to methane, CH4, and CO2, carbon dioxide. Then the experimentally derived rate equation for the above reaction is given as R equal to K, bracket open, CH3, CHO, that's ethanol in bracket, because of ethanol raised power 2. And we have to state I, the order of reaction, II, the molecularity of the reaction. So solution, you say in the given rate equation or law, the concentration of ethanol CH3CHO in square bracket is rate power 2. Hence, the reaction is second order. If you look at the rate law, look at it. You see that the ethanol raised power 2. The order is the exponent there, as we had defined before. So this is a second order reaction because ethanol raised power 2 in the rate equation. So the concentration of ethanol raised power 2. So you can see that. So that is why it's a second order reaction. Then II says find the molecular reaction. We go to the chemical equation. Look at the reactant side, not the product. You ask us how many molecules of ethanol is involved. Only one molecule of ethanol is involved in the reaction. And that makes the reaction a unimolecular reaction. So we say only one molecule of reactant ethanol is involved. So the reaction is unimolecular reaction. So that brings this session of our video to an end. So the next tutorial class we're going to have on physical chemistry will be on derivation of integrated forms of rate equations and their subsequent calculations. So stay connected to the channel. If you are not subscribed to the channel, tap on the subscription button, get subscribed and follow us as we'll study online on chemistry and other latest science subjects or courses, including the practicals. So stay connected and thank you for listening. Share videos to people that need it. Thank you for listening. Thank you very much.